We'll talk today about congestion pricing in Bangalore. Let me start by saying that until a few weeks ago, and hopefully again in some time, traffic congestion was a large problem in large cities throughout the world. And this hits cities and megacities in developing countries particularly because they grow, they are growing fast in terms of population and in terms of private vehicle use as well. And this growth is fast relative to their infrastructure. So Bangalore, which is the setting of the study, is quite slow. It's a bit basically on par with central Manhattan, and this paper by Akbar et al. Ranks it as the slowest city in India. Now, as economists, when we hear traffic congestion, I think a lot of us think about immediately at the externalities that driving costs, and the fact that this leads the current equilibrium to be inefficient. In this paper, I will focus on a particular dimension of this externality. So I'll be looking at just the speed aspect. So if I drive my private vehicle on the roads, it's going to slow down everyone else. I don't take it into account, and so there will be too much congestion and equilibrium. I will not have anything to say about other important dimensions such as air pollution, accidents, and so on. Now, theoretically, we know how to solve this. We just need to realign the private and social costs, for example, with an appropriate monetary charge that's commensurate with this difference. Now, the question I'll be looking at broadly is how large this inefficiency is in a city like Bangalore and how an optimal allocation would look like. This is not obvious. So the fact that traffic is slow in general does not immediately tell us that it's also significantly inefficient. This is something that, it trivially depends on everything that comes together here. So the size and shape of the externality and the preferences of all the traffic participants. Now, going into this, we actually don't have, there's a wide range of possibilities. There are models that suggest that traffic congestion should be zero, so there should be no delays in the social optimum. That's the bottleneck model. Or you could imagine a setting where there's somewhat less congestion, but still an optimal amount of it under the optimum. So this is broadly the question. And I will study this in the context of the peak hour traffic equilibrium. And so this graph shown here shows average travel times, travel delay. So this is the inverse of speed. This is how many minutes you need to advance a kilometer for different departure times as a function of departure times in Bangalore. This is Google Maps data. So to give you a sense here, the base is around 2 minutes per kilometer. That's 30 kilometers per hour. And then at the peak hour, this is the delay is double, so speeds are half as much. So that's 15 kilometers per hour. And so I will study how the allocation of drivers around this peak hour. We feel that there's too much traffic going on there, and optimally drivers should be some of them should be perhaps traveling earlier, some later, in order to take as they take into account the cost that they exert on others. Now, I will study this particular problem holding fixed certain margins of adjustment. So in particular, people won't be changing. I won't think of how people choose where they live and where they work. And I'll hold fixed the fact for the most of this talk, the fact that they are using a private car. So you can think of this as a subproblem of a series of more general problems in urban transportation. So you can embed it into the decision to use a mode and the decisions where to live and work. For example, like Nick Tsivanidis' work with Transmilenio in Bogota, where that impacts the entire structure of the city. So there are two reasons to focus on this margin. The first one is this intuitive idea that congestion pricing and traffic externalities should be priced precisely. We shouldn't have like just a flat tax on cars, but should be zooming in on where congestion is higher. And looking at departure time is a first step in that direction. It's not as precise as you could imagine, but it's going in that direction. The other reason is practical, which is I'll show you results from an experiment. And I'll argue that departure time choices are informative about people's preferences. Even in a short, the way they change their behavior in the short run is informative about their longer term preferences as well. So the research question I'll ask is, what would be the impact of congestion pricing on travel behavior as well as a measure of commuter welfare? And so to do that, I will proceed in 4 steps. I'll start by setting up a model where the main margin of choice is departure time. And I'll highlight the 2 relevant preference parameters that are key here. The first one is how commuters value time spent driving. And the other one is how flexible they are, how strict they have preferences about when during the day to travel. So those are going to be some schedule costs of arriving earlier or later than ideal. The next step will be collecting data that is commensurate in precision and detail to the decision margins in the model. And so this will be using a smartphone app.
Gabriel, we've got a clarifying question here, which is from Carlos Hurtado. Could we use a ban on cars, as in New York here?
So in general, we can use a ban on cars. In the model, this is not going to be something that is going to be relevant. So in the model, I will keep fixed for most of this talk, except at the very end, when I'll come back with some counterfactual simulations. The amount of private vehicle travel is going to be fixed. I'll be looking at the allocation at different times of the day across departure times. So you can think of the problem here as like, what is the optimal amount of flattening the peak hour in Bangalore?
Right, we've got another one just come in just while you were speaking, which is whether you are assuming that drivers in peak and off-peak hours have the same price sensitivity.
Let's talk about that when I show the model. Great. So informed by the model, the third step in this in the project is to design a field experiment, a randomized field experiment with congestion charges. And so there will be 2 types of congestion charges. First, the first one is a peak hour congestion charge. So it most intuitively sees how commuters respond to having it be more expensive to travel during the peak hour. The second one is an area or a route congestion charge. I'll explain this in more detail, but the key contribution here, the key idea is that it introduces a trade-off for commuters between taking a short but expensive route or taking a longer but free route. And so these, how commuters respond to these congestion charges will help estimate and identify the preference parameters that are key in the model. And so I'll show you reduced form results, but also an estimated discrete choice model. Now, so far, and for half of the talk, this will all be about the demand side, about commuters' preferences. However, to say something about optimal congestion charges or the inefficiency in the current equilibrium, we also need the other side. So in the last part of the paper, I'll do 2 things. I will use the GPS data collected to measure the road traffic externality in Bangalore. And then I'll put it together, so the preferences and the externality. I'll allow congestion to be endogenous in a model of the peak hour traffic equilibrium. And so in that model, I'll be able to answer these questions and also conduct other counterfactuals. So without a preview, because of the duration of the talk, let me jump into telling you about the data. So to collect precise data on these decision margins of departure time and route choices, I partnered with a small startup to create a simple smartphone Android app that collects precise data about location. So the way this works is that study participants install it on their phone, and then passively the app works in the background and collects location data every 30 seconds or up to 5 minutes. And then at regular intervals, it uploads it to a server. Now, smartphones in this setting are fairly prevalent among drivers, car and motorcycle drivers in Bangalore. And so this covers a lot of the sampling frame. Now, this data is kind of, when it's collected, is very, very precise. It's also by no means perfect. So participants need their GPS to be switched on their phone, and sometimes internet as well. And so during the experiment, we reach around 3/4 of the days when we have kind of quality data about their behavior. So this data, once it arrives on a server, is automatically coded and cleaned. And so the first step is to clean kind of outlier points from it. And then the important step is to automatically transform it into trip data, where there's a departure time for each trip, an arrival time, as well as a precise route. And so here's an example for one commuter on a particular day. So the setting of the study is the city of Bangalore. And in particular, the way we recruited study participants was to send surveyors to randomly chosen gas stations in South Bangalore, which is shown here. So surveyors then approached, so gas stations were chosen as a kind of practical decision as somewhere where more or less anyone who commutes and driving a car or a motorcycle will have to pass through at some point in time. And the way this worked is that surveyors approached randomly, or either a car or a motorcycle driver, not taxis or other professional drivers, but their target audience was commuters who had a vehicle. They used a flyer and a well-rehearsed script to invite participants in the study. And so the flyer invited them broadly to a study about traffic congestion. It also mentioned in rather vague terms that they may receive at a later stage incentives for changing their travel behavior. I mentioned this as this may be relevant a bit later. And so if people accepted, they then installed the app on the spot, as well as responded to a short survey. Let me tell you a bit about the timeline of the study before giving more details. So this was the recruitment stage. And after that, we collected GPS data from their app for an initial baseline period, after which there was an in-person meeting between a surveyor and each study participant before they entered an experiment, which lasted for 5 weeks, approximately. And so, as you may imagine, compared to the number of drivers that we approached, only a small percentage, around 6%, ended up enrolling and most of them completing the experiment. So questions of selection of this sample of study participants compared to the entire population of commuters in Bangalore are first order. So we want to know if the preferences of commuters in the experiment are representative of all drivers. So I'll tell you almost everything I know about this results. Let me just defer this kind of addressing this quantitatively then, but I wanted to acknowledge it here. Okay, so I do want to say something about travel behavior as measured by GPS data at this point. So in this sample of around 500 commuters, on average, people make around 3 trips per day, which are the median duration of which is half an hour and 7 kilometers. Now, 3/4 of them have a regular destination that they return to almost every day. And in panel C, I want to say something about departure time variability. So this is the kind of the key margin in this paper, and this is something that previously we knew little about. So what I do here is I look within a person and within a destination. So for people who commute to work, in the last row, at the first trip from home to work on a particular day in the morning. And I look at the variability, the standard deviation of their departure time. And so this is on average more than half an hour. And this looks similarly for the entire distribution. So most people have a lot of variability in when they travel, even within a particular type of trip already. And so this is, this is something that may indicate that they have a lot of flexibility to change when they travel, but it's not at all conclusive. It could be that every day they just have, they have different types of tasks that they need to do in addition. And so sometimes they need to arrive early, sometimes they need to arrive late. And so the experiment that and the model will clarify kind of how this distinction works. And the experiment will help answer this question of whether this is real flexibility or not. Okay, so before I start on the model, I want to say a few things on the logistics of how a congestion charge experiment worked. And so in order to charge study participants and to take money away from them, we first gave them money in a virtual account. And then automatically, while they were in the experiment, congestion charges were deducted from them. At the end of each week in the study, in the experiment, whatever was left in the account was transferred to them as a bank transfer. So these were real money, and all of this was explained ex ante. Now, throughout the experiment, they received messages explaining how much they were charged, why, and how to avoid these kinds of charges. And all of this was done automatically. I want to point out two additional and specific features specific to the experiment. So there were additional penalties for providing no GPS data. So if someone accidentally or intentionally switched off their phone for a prolonged period, as well as for making no trips. And the reason was that this experiment is really not designed to induce less travel, because I would be very skeptical of interpreting seeing fewer smartphone trips as necessarily meaning fewer real trips. So this was explicitly disincentivized. Not to a full extent, but if there were no trips during half a day, then there was this additional charge. Okay. So now let me start explaining the model and the experiment. As they are intertwined, I'm going to be going back and forth between the two. First, I want to step back and to acknowledge that kind of urban travel demand is a problem with many layers. So you can think of people choosing where they work and where they live, as well as the mode of travel. And then conditional on those, they choose the key thing I'm focusing on here, which is when they make their trips, so their departure time and also the routes that they use. And so I'll be focusing on these highlighted margins. You should think of the following problem in what follows. A commuter has decided to go from home to work and is choosing their departure time. Now, the environment that they face is that they know that at each departure time, there is a different travel time distribution. So there's an average travel time they can expect, which maybe is lower in the early morning. There's also maybe more uncertainty correlated with longer travel times. So let me first outline the problem kind of simply, and then I will explain the full model and what we want from it on the next slide. So let me describe the utility for one commuter here. So here, U is going to depend on the choice variable, the departure time H, as well as the realized travel time, capital T. And it's a quasi-linear in money, so monetary congestion charges are going to enter linearly into this function. And it has two components. So first, there are preferences over average travel time, and these are specified as linear. So alpha is the value of time spent driving. The second part, these two terms, is the canonical way of modeling schedule preferences. And so this works as follows. Each commuter has an ideal arrival time, HA, and if they arrive at that time, so H plus capital T is exactly HA, then they incur no additional costs. This is what they want to do. However, if that doesn't happen, if they arrive early, they incur a linear penalty per unit of time, beta E. And if they arrive late, they incur a penalty, beta L. So they have, these preferences have these linear shape, and arriving late and early may be different. So the whole goal of the experiment and what we want from this model is to learn about these preferences, the value of time, and the schedule flexibility. So this is kind of highly parametric model, and in the paper I discussed this more. It's also commensurate with kind of what I'll be able to learn practically from the experiment. Now, let me add a bit more nuance to this by saying I is a commuter and T is a day. So projecting this onto the panel dimensions of the data. In practice, this will be a logit type model. So there's also an idiosyncratic preference term here that depends on departure times. And one way to think about the problem is to notice that travel times are akin to observed prices. I'm going to use Google Maps data to actually describe people's choice sets. And we want to learn something about the alphas and the betas are akin to kind of price elasticities. However, one problem is that there are also these unobserved ideal arrival times, which are going to make this problem difficult. And so I'm further going to allow a lot of flexibility in this ideal arrival time. And so here for each person I, there is an individual specific distribution. And every day they get one draw, they observe the ideal arrival time, and then they make their decision. But we do not observe any of this. And so that makes it difficult to kind of identify the alphas a bit. So to cut through this problem, what I will do is introduce experimental variation along two dimensions. One is departure time, H, and the other one is travel time, so the capital T. So now let me switch to describing the two congestion charges. And I will start with the departure time congestion charge that creates price variation in H. So this is what study participants in the departure time treatment saw. That they received this kind of paper laminated card, just like the one you see here, one for the morning and one for the evening intervals. And they were explained the following script. So each trip that you will make during the duration of the experiment will be charged with a per kilometer rate. That rate depends on the departure time of the trip, as indicated by this graph. So there are off-peak periods, there are peak hour periods, and crucially, there are two periods where the rate is steadily increasing, and then one where it's steadily decreasing. And so these areas create marginal incentives to either leave a little bit earlier or leave a little bit later. There were 4 sub-treatments as part of this treatment. So there was a control group that just received a flat payment for participating. There were a low rate and a high rate, so just varying the magnitude of this profile. And there was also a sub-treatment that I call information and nudge, which included all of the components of the treatment, except for the monetary incentives. So people were paid a flat amount. However, they received daily SMS reminders, as well as kind of an information about congestion, which was similar to how this graph looks like. So Clémence, I see you have a hand raised. Do you have a question?
Yeah, thank you. Sorry, just quick clarifying question. How do you charge them practically? Like how is the money flow going? Great.
So they have a virtual account set up. So with an initial grant, then the charges are subtracted out of that. And then whatever is left into their virtual account at the end of each week gets transferred with a bank transfer for them for real. There was also some kind of, to build trust, initially there was a trial period of 3 days, and there were some welcome kind of initial bank transfers just to make all of this more tangible and credible.
So it's about winning less, not really losing from.
You can, so that's a great point. It's possible that people interpret it this way. We try to frame it as this is, so the script for the surveyors was, this is your money, and now you decide how to spend it. But you're absolutely right that exactly how people framed it is, I'm not 100% sure. One thing to mention there is, this is akin to how easy pass accounts, how in reality, how a bunch of these tolls work. Their salience and how much it's mental accounting that you put a bunch of money in an account and it's subtracted from that is I guess a feature of real policies as well.
Thank you.
Thank you. Thank you. So intuitively, how commuters respond to this type of congestion charge relative to without is going to be informative about how strong they have schedule preferences, so the magnitude of the beta parameters. However, the value of time is also tucked in there. So if people decide to leave earlier, that decision also affects the amount of time they spend in travel. And so that is monetized by alpha. So that's why we need a second experiment, which I'm going to introduce now. To introduce it, I'm slightly going to enrich the model. So imagine, in addition to the departure time choice, there's also a route choice. And commuters have two options. They can either take a short route, r equals 0, or one that is longer. Let's call it r equals 1. The treatment that I have in mind is a flat congestion charge for the short route, which creates this trade-off between going fast but having to pay for it, or going slightly slower on a longer route, but getting that for free. And so this is mostly going to be informative about alpha, although, as mentioned, everything is interconnected here. So we're going to need both treatments. Let me tell you how this happened in practice. So for around half of the experimental participants, with the baseline data, we were able to identify in the baseline data a usual route from their home to their typical destination. Now, I had an algorithm choose a congestion area that obstructed that usual route and created this option of either of a detour route, which was slightly longer. And so commuters were told any route that avoids the congestion area is not going to be charged. And in particular, here's one example, which we believe takes, for example, 5 minutes more or 10 minutes more. So this was an individually tailored kind of chosen congestion area. And as mentioned, so intuitively, people's choices in this setting are going to be informative about how they value this additional travel time in the detour. So this is all partly intuitive, but also partly heavy as in terms of explaining all of this. So a surveyor met in person with each study participant and went through all of the steps of the treatment to make sure that they understand and that all of their questions are answered. And this was done before the start of charges. Now, in terms of design of the randomized experiment per se, I want to highlight one thing mainly. So the timing was as follows. So the area or route congestion charge was never happening at the same time as departure time. It either happened for random subset initially, the first week of the study, or for the others, the last week of the study. And so actually in the area comparisons that I'm going to show you, there will be no pure control group, and I'll be comparing these early areas to these late areas. In the departure time, this takes up the remaining period of 3 weeks. Now, we also had a survey, so just to give you a sense, a survey during the experiment, and where we found that broadly around half of the participants remembered key features about their congestion charge and treatment. So you should keep that in mind. Okay, so let me start with reduced form results. And as promised, I'll start by saying something about selection. So in this table, I compare the around 500 commuters who are in the experiment with everyone who we approached, especially in panel A. So this is around over 8,000 people. So the first observation is that in Bangalore, car and motorcycle drivers are overwhelmingly men. This is true of everyone that we approach, not only those who end up in our sample. And this is kind of highlighting the mobility challenges that women face in cities like Bangalore and countries like India more generally. In terms of variables that we have for everyone, even people who did not even want to talk to our surveyors, we noticed that people in our experiment are younger, around 2 years younger, and they are slightly less likely to be car drivers, 30% in our sample versus 40% in general in gas stations in Bangalore. Interestingly, the value of the vehicle, residualizing car versus motorcycle, is there's no difference there. Now, on a smaller sample, we have people accepting to participate in a survey, but saying no to the app. And so there we can do some further selection checks. we find no difference in self-reported income and some slight differences in stated preferences. And so these are preferences that map onto the experimental dimensions. The big caveat here is that these stated preferences are not predictive of what actually happens in the experiment. So for people for whom we have both the stated preferences and the experiment, these things don't correlate. This may be due to lack of power, but I guess this raises some questions about stated preferences more generally. Okay, so let me switch now to how commuters responded to the departure time congestion charge. So what this graph shows is on the x-axis is departure time relative to the trapezoidal shape of the congestion charge they receive. So that is shown here in blue, and departure time is relative to that. And in red is the difference in difference. So the experimental impact on trips by departure time. So it's essentially the kernel density of trips in the 4 groups before, after, control versus treatment, and then taking the diff and diff of those. And there are 3 things to notice here. So one is that overall, this red line integrates approximately to 0. So this means there was no change in the number, the aggregate number of trips due to the to congestion charges. The second is that during this early period where the price is steadily increasing, there's an aggregate shift in the mass of trips towards earlier, cheaper times. So this is actually made up of small changes. People, some people are responding less, but in aggregate, it shows up as fewer trips when it's expensive.
Gabriel, we've got a clarifying question, which from Johannes Bohm, as to how you know the income of the people that didn't sign up.
So that comparison is only among people who accepted to participate in a survey, but said no to the app. So I don't know the income. The value of the vehicle is the kind of the best proxy for income that we have for everyone. And other than the car motorcycle difference, there's no change there. Okay. And so the third thing to notice is, there's something that looks like a faint symmetric response in the late morning. So people, a move of mass towards later times when it's cheaper. Although this turns out to not be quite as robust a result. So these results were focusing on regular commuters and focusing on home to work trips. When we look at all trips, the early morning result is kind of very robust. Then what happens in the late morning is not. You see something that's more consistent with a discrete change in non-commuting trips, which I will not explore further in this presentation. So let me show you these results again as a regression. So here, the outcome in the first 2 columns is what I call shadow rates. So I want a summary statistic of behavior that leads to more expensive congestion charges. And so this is calculated for every participant, whether they're control or treatment, and for every time period in a uniform way. And this way, it is a summary statistic of whether people change their behavior in order to incur fewer congestion charges. And so from this unitless control mean of 100, in the high rate subtreatments, we see a decrease of around 15%. Nothing significant for the low rate subtreatment, and also very close to 0 and effects of just providing information and nudges. So this part suggests that it's really pricing is the differential that makes people in the high rate treatment to change their behavior, not the whole package of reminders, experimenter demand potentially, etc. And so for the rest of this talk, I'll kind of bundle the high and low rate together and the information and the control. Now, these shadow rates are a combination of intensive margin and extensive margin. And so in the last 2 columns, I show that these decreases are not because of commuters making fewer trips. These coefficients are not significant, and their magnitude is significantly smaller. So switching to how commuters respond to area or route charges, I show a similar table. Now here, shadow rate means that people are charged this shadow rate 100 if they travel through the congestion area, if they make a trip that intersects the congestion area, and that measure falls by around 25%. And if you remember, so these were there's no pure control group. We're comparing people who got this early to those who got it late, and so even when we look between, so the comparison is we see an effect in both weeks. As for departure time, we're interested in an intensive margin change. So the part that will be interesting is to see whether people make longer trips to avoid it, and not seeing them make fewer trips overall. And indeed, there's no evidence that being charged leads people to make fewer trips. In fact, there's a positive coefficient. And this turns out to be because in the last week in the experiment, commuters in the control group tended to leave the study more. And so the ones in the treatment group have higher number of trips. But overall, this is all consistent with intensive margin changes. Okay, I will say about heterogeneity, I have kind of two key points to mention. The first one is that there seems to be two types of commuters, some who respond significantly and some who don't do anything much at all. And secondly, that unfortunately, I don't have the power to pin this down to observable characteristics. So I documented, but I cannot say whether this is due to income or self-employed commuters, etc. Those results are not robust. So having shown something about in reduced form how commuters respond to these two charges, I now turn to estimating the two preference parameters that are of interest: the value of time spent driving, alpha, and the early and late schedule costs, the betas. In order to do so, I estimate the discrete choice model that I set up initially using the experimental variation. And so the model that the model, just to recap, is a choice over departure times as well as a choice over routes. There's a short and a long route. I overlay over this an error, an idiosyncratic preference terms that lead to a nested logit structure here. In addition, because of the heterogeneity results that I just mentioned, I overlay a discrete form of heterogeneity. So commuters in this model are going to be attentive to congestion charges with a probability P. And with the rest of the probability, they're just going to ignore them. So they're going to behave as if congestion charges are not there. So the way I estimate the model is with a generalized method of moments, using a particular set of moments that leverage the experimental variation. So these moments are, there are 4 sets of moments. 2 for departure time. So departure time market shares, how many people use different departure times. These map onto the graph that I showed of the change in when trips happen, as well as moments related to departure time heterogeneity, how different people respond. And similarly for route choice, one set of moments chooses the how many people avoid the congestion area, so choose the long route. And then a set of moments which looks at the heterogeneity between people in that choice. Now, all of these are for control group and for treatment group, hence leveraging the experimental variation. Let me show you the results from estimating this model using the behavior in the experiment and choice sets constructed using Google Maps for each commuter. So the key result here is that I find a high value of time. So I find alpha to be around over 1,000 rupees per hour. That's around $17 US. And that is very large compared to the hourly wage reported by commuters in this sample. So a few observations about where this comes from and what it may mean. So first, I want to emphasize that this is identified from the choice between the typical route and a detour route. So in particular, this might be embedding a fixed cost of switching to any route. And so that's something to hold, to keep in mind, that the sub-treatments were kind of designed to that I mentioned here were designed to address, but unfortunately they don't have enough power to actually estimate a fixed cost and to separate a fixed cost from a variable one. There are other reasons why this value will be large. One of them is just a lot of so one of them is that this is time relative to Google Maps, and commuters in the sample, I document that they overestimate travel times. So if Google Maps says leaving half an hour is 5 minutes faster, people will tend to say to believe that it's 10 minutes faster. And this applies to the detours as long. People think the detours are longer than what Google Maps thinks. And so if you adjust for that, then this would be a lower value. So apart from the value of time, the second key result here is that schedule preferences, so the cost of leaving early, the cost of leaving late, are around 4 times lower. And this means that there's a fair amount of flexibility in terms of how commuters decide when to travel and how costly it is for them to be induced to travel at different times. The probability to be attentive to the experiment is around half, which is very close to what I find in survey evidence. Okay, so far this part has documented in terms of preferences that commuters in Bangalore value time spent driving very highly. This is something very costly for them. And in relative terms, they have a fair amount of flexibility to change when they travel. Now, this by itself doesn't tell us anything about the inefficiency in the traffic equilibrium. So for the rest of the talk, I will switch to describing the externality, the other side of the equilibrium, and putting it all together. So what we want is, in a citywide traffic equilibrium, to allow the profile of traffic congestion to be endogenous. And this is what I will do here. So if you imagine a congestion charge, this will move in aggregate commuters, and that will change travel times at different times. And so I want to model that and to understand it. I'll do so in 2 steps. First, I will show evidence on the shape of the externality in Bangalore. And second, I'll put it all together in a simulation model. Now, I continue to make, yeah.
Sorry, clarifying question, in fact, on the previous slide. So we'll just raise it here quickly from Moritz Boll as to whether you have data where the detour is exactly as long as the original route, which might help you to back out the fixed cost of switching route.
Sorry, can you repeat that?
Do you have data where the detour is exactly as long as the original route in order to potentially help you back out the fixed cost of switching route?
I have data on the distance. It's something that I haven't explored. I guess the concern is that there's still a fixed cost, maybe mental or due to habit or due to unobserved preference heterogeneity to take this particular route. And so that I cannot address only with same distance. But that's right, that some of these longer routes in time are actually shorter in distance. Thank you. So throughout this model that I'm going to show, I continue to make these kind of simplifying assumptions and focus on this decision. So just looking at the traffic equilibrium. So in order to understand this, let me first tell you about how traffic volume in Bangalore affects travel time. That is to describe the externality. So I will do this at higher trips. So the travel time experienced on the full trip, as well as the number of trips. So I'll measure volume at the level of the number of trips happening at a particular time. And to do so, for volume, I'll be using all of the GPS data that I collected. So this is everyone in the experiment, but also additional participants and everyone before the experiment. This is around 120,000 trips. And for travel time, I use 2 data sources that give very similar results. I can either use Google Maps real-time data that I collected for 6 months, every 20 minutes, on a fixed set of routes, so kind of fixing the routes choice part. I can also use the travel time directly from the GPS data, and those results are similar. One caveat is that I can't distinguish the externality of a car from an externality like the effect of a motorcycle. This is very important, but I won't have anything to say there. So let me show you, this is the main result, what this graph shows. So on the x-axis is normalized traffic volume. So this is, sorry, let me say, I take all the traffic volume data, and then I summarize it at the level of departure time. So I take the average volume at 8 a.m. over all the weekdays, non-holiday days in the sample. And so this is what a point over here represents. On the x-axis is the traffic volume. And on the y-axis is the Google Maps travel delay, so in minutes per kilometer. And so doing this leverages the huge difference in traffic volume on average throughout the day. So this is a very repeated situation. And in general, at 8 a.m. or 9 a.m., as well as in the evening, traffic volumes are consistently high, especially compared to other times of the day and during the night. And so what I see here is a very linear relationship. And the slope of this relationship suggests that at peak hour, a person making an additional trip of around half an hour generates 17 minutes of travel time extra for everyone else. So of course, one trip generates epsilon, and then this is multiplied by everyone that is impacted at that time. And so I do, this is something that I need to interpret causally. So I want to make the case that this relationship is informative about the causal relationship of traffic volume at a particular time of the day on travel times. So the main concerns to interpreting it this way are, one, that in this sample, so the traffic volume I have is in the sample of smartphone users that I recruit. So in that sample, peak hour volumes are perhaps overestimated. So the real shape actually looks more convex and the externality is higher. So I should say this level of externality is small compared to what transportation engineers find, and also kind of our intuition. This is it's a significant cost, but we in traffic congestion previous models, we think of the social cost potentially being several times larger than the private cost, whereas here in this back of the envelope calculation is around 50% of the private cost. So we're concerned whether this is actually in reality a more convex relationship. And so one way that it could happen is if actually in this sample volume during the peak hours is overestimated. So in the paper, I do some exercises to convince the reader that this is not the case. So when people are recruited in gas stations, for example, is not informative almost at all about when they actually conduct all of their trips at later times. People are and this goes back to this large variation in when people actually travel in the sample. Another concern would be that traffic is faster during peak hours for unrelated reasons. And so it's just a different supply curve during the peak hour. And it's not the volume that's generating we're not really identifying the supply curve here by varying demand. There are multiple supply curves. So, and I further discussed this in the paper. There's nothing that strikes me as extremely compelling as an argument for this. And I do several exercises, such as looking at particular trips. So a trip level regression where I control for trip length, other trip characteristics, and the identity of the commuter. And this relationship stays the same. Some further robustness checks that I do and that are described in more detail in the paper are, I look at this relationship not across departure times, but across calendar days. So essentially comparing things like weekends and holidays to normal weekdays. And there I find, although the range is much smaller in average volume, I find a very similar relationship. I also zoom in at the artery level, and there I find even within major arteries in Bangalore, I find very similar results. So broadly, this is different from what I thought of externalities going in, and what the traffic engineers especially show on highways in the US. And so the hypothesis is that this type of relationship is specific to urban road networks, such as Bangalore's, as they are different from highway control access highways in developed countries. And I have a couple of models that kind of make this intuition precise of why we would find exactly a linear relationship in this type of networks. So in the last part of the paper, I want to put together the two previous parts. So I'll have agents endowed with the preferences estimated from the experiment, choosing their optimal departure time, facing an environment where they face a travel time profile, which is endogenous and which is determined by the externality that I just described. There are two important objects here. One is the current unpriced Nash equilibrium, which we think is inefficient. And the second one is the social optimum. So this one, I find this as a Nash equilibrium, which has Pigovian congestion charges. So each person is charged the marginal social cost of making a trip at that time of the day. And I will show the best case scenario for congestion pricing in these simulations. So in particular, there are no implementation costs or running costs, and all of the revenue from the congestion charges is recycled to commuters, back to commuters. And here are the results of how the Nash equilibrium looks like in dashed black lines. So this is the profile of traffic congestion in the morning. So this is travel delay on the y-axis, and then from 5 a.m. to noon in terms of departure time. And we see something close to what I showed initially in Bangalore of a morning peak hour around 9 a.m. In red, I show the same travel delay for the social optimum. And so because traffic volume translates linearly into traffic travel delay, this is also a representation of where the volume of trips happens. So what you can see is that there's less of a peak hour, and then I can tell you that in the social optimum, people generally leave a few minutes earlier than they do in the Nash. And in aggregate, that translates to this shift of mass from the peak hour to early morning. So these are not individuals switching a few hours earlier, but in aggregate, shifting everyone or many people back. And so this actually looks quite similar to the Nash. And this will be the punchline of these simulations, is that there are some travel time improvements. So in this table, I look at the Nash equilibrium where a home to work trip is on average 40 minutes and 38.7 under the social optimum, which depending on which benchmark you use is between 4 and 9% as an improvement. However, commuter welfare in this model is not only travel time, it's also their schedule costs. And so in the last two rows, I look at commuter welfare in rupees, and that improves in the social optimum by a much smaller amount. So when you put it together, the social optimum has this slightly different shape, with these notable but small travel time improvements, and a very small improvement overall in terms of commuter welfare.
Gabriel?
Yes.
Sorry, I have to. I can't raise my hand on the. So I interrupted you right away. I had a quick question. So you said you keep the residential and workplace locations of these people essentially exogenous and fixed in the model. Yeah. I was wondering whether, so if you allowed people to say adjust their residential location, my guess is that it would lower these welfare gains even more, because through the housing prices would to some extent incorporate the congestion effects. The externality, and so is that correct, that it would close that welfare gap even more before the decentralized equilibrium and the planning solution?
To be perfectly honest, I've tried several times to think of it in a kind of model, and Nick and I have talked, I guess, a couple of times about it. I think you would want to include it in a model where the people choose their homes and works, and then you also want to allow for heterogeneity in income, right? So that people who have higher and lower value of time are affected differently. And I just don't have a great intuition for what will happen overall in that model. Yeah, I'm sorry that's the best that I can say.
No problem. Thanks.
I will say one thing which is relevant right exactly on this slide, I hope. So I think the last thing I want to do in this slide is to understand, using counterfactual simulations, where these small welfare gains are coming from. And so they could be coming from preference side or from the externality side. So the first thing I do is changing preferences essentially varying the value of time, either from anywhere from 4 times smaller to 4 times larger than what I find in the experiment. And I see that that actually does not change these, it changes the equilibrium, it changes things about the Nash equilibrium as well as the social optimum, but the relative improvement of one versus the other doesn't change much. The key thing, and the other thing that I do is introduce preference heterogeneity, so allowing in different ways for people to have different values of time and different schedule costs in the same amount as there's variation in the wages they report. And again, I don't find large gains, very similar relative gains. The one thing that I show is extremely important in driving these results is the linear and kind of shallow road technology. So putting a cubic relationship in sort of the linear that I showed makes a whole difference, and leads to 1 order of magnitude larger welfare gains from optimal congestion charging. And the last thing I want to mention, which goes a little bit, but not enough in Adrian's direction, is I incorporate an extensive margin in this model. So I allow people to just drop out of traveling, cancel trips, with no externality if they do so. And so there I document that this depends on the trip elasticity. So the welfare gains are increasing for this, the higher this extensive margin elasticity is, as you would expect in a very standard simple model. And quantitatively, you would find an order of magnitude larger welfare gains if you have an elasticity that's above 1 in terms of the probability of making the trip elasticity relative to the total travel cost. So that's something that I don't have data and kind of evidence to benchmark, but I guess you can use your priors of whether this is a reasonable responsiveness at the extensive margin or if this is too large. So I want to conclude by going back to the idea of charging congestion very precisely. This is a very appealing idea. The technology now exists to do it. However, whether and how much it would improve things like commuter welfare or cities more generally is a quantitative question. And so what I show here is that in Bangalore, peak hour pricing is less attractive in terms of ameliorating speeds at the cost of disrupting schedules than at least I believed in initially. I think, of course, that there, as Adrian mentioned, housing, but also other important margins of externality that and response that are not included here that may very well overturn this. And so I want to be precise about what I think this is showing. Thank you.
Terrific. Thank you very much indeed, Gabriel. We've got a bunch of questions here, and I will go through them in small groups as we discussed. For the benefit of those whose questions we may not turn to, because I know there's a lot of interest and a lot of questions here, Gabriel will receive a full readout of all of the questions asked, and of course feel free to follow up with him by email. Apologies if we don't get to your question. We will take them in the order in which they appear, which is based on the upvotes. So there's a couple of questions, related questions from Johannes Berman and Camilo Acosta about whether, if we're implementing a congestion charging policy of this nature, we might expect a firm response. So for instance, employers becoming more flexible regarding working hours, and therefore a change in the cost of being late for work, and how you think about issues of firm responses. Don Davis raised the question of whether the structure of the pricing, in particular an endowment less the charges, might induce concerns about loss aversion. So you talked briefly to this in your response to Clemence's clarifying question, but whether you had further reflections on that. And then a question from Emilia Esperon about how you chose the congestion area and whether you might be able to talk a little more about the algorithm. So I will pause there to let you answer those before the next group of questions.
Wonderful, thank you very much. So let me take these in turn. So this is absolutely right. One assumption here is that firms do not respond. And so there are two things which are kind of, well, the ideal arrival time distribution, I assume, is fixed in the presence of congestion charges. And so there are two things that may change in the longer run. One is firms may be more lenient for someone arriving late. And so that there are two ways to model that. One is as a change in beta. The other one is that firms might actually change for particular workers, or in general, they might change when they expect workers to arrive. So they might change their entire schedules to have staggered hours in order to kind of help workers avoid congestion charges. And so neither of those are allowed. And I think they have different effects on the conclusion. So the changes in beta, I don't think would make a difference in the argument in the headline conclusion that welfare gains overall are going to be small with congestion pricing. The reason for that is that exercise is very similar to changing alpha. It's just kind of changing the relative magnitude of preference for value of time versus schedule. I think changing ideal arrival times is a different story. So that's something that I have not done an actual counterfactual with. It's something I can do, and I guess based on discussion, I should do in this model. My intuition is that may change welfare more, because people are even in this model. The size of the betas is such that in the end, people are still relatively inflexible around their ideal arrival time. So they have this flexibility of a few minutes before and after, but in the scheme of things, in the size of the peak hour, that's small. Now, I think that's also a super interesting question because it raises other externalities. So firms staggering their work hours also raises questions about coordination between firms. What are the losses from them doing that? Some firms starting at 8 and some firms starting at 10 a.m., for example. So the second question about the endowment effect. So I completely agree that the framing of congestion charges, I think this is an established fact that in general taxes and congestion charges in particular, responsiveness to them may depend a lot on how these are framed, how salient they are. And so I think it may very well be that the responsiveness would be different with a different type of framing. That said, again, I think I show that the magnitude of these preferences in this final simulation model is not what's driving the final conclusion. And finally, I'd love to say a bit more about the algorithm of how these congestion areas were chosen. So if you remember from the baseline data, we had a commute, like a typical route for a certain person. The algorithm chose several candidate areas of given radiuses along that route. So those are kind of pre-specified at certain locations and different radii of 250, 500, or 1 kilometer. And then for each of those, I had a modification for Google Maps kind of travel time to find the shortest path from A to B that avoids the circle, the congestion area itself. And so among all of those, I classified the candidate areas that created a reasonable detour, something between 3 and 14 minutes, and then randomized between which one of those actually gets implemented. And that's how, in a subtreatment that ultimately didn't work, I got random variation in the detour that people were exposed to.
Terrific, thank you. So I will ask another batch of 3, and then I will turn for the final batch to the panelists. I can see they've got raised hands and they're not able to use the chat functionality. So apologies for those with questions further down the list. As I say, I'm sure Gabriel would very much welcome emails with for additional discussions. So there's a group of questions. Don Davis and then Vinyat asking about the magnitude of the cost of travel time estimates. So traditionally in developed countries, this is viewed as much lower than the hourly wage. Why should we expect it to be so different here? So you touched upon this briefly. Perhaps you could reflect on that a bit more. A question from Christian Dubin. So it might be that many study participants do not commute alone. So if there are other people who are not receiving the incentives in the same vehicles, relatives and so on, this might also influence the chosen commute times. So how do you think the results might be different with more vehicles in areas with more vehicles per family, for instance? And then the next question on the list is how far you've taken into account commuters' fuel expenses in the choice of taking either shorter or longer routes. So in the interest of the fact we've only got 5 minutes left and I want to allow some time for the panelists' questions, I'm afraid that's where we will cut the questions from the list, but we look forward to your responses.
Wonderful, thank you very much. These are great. So the value of time, I discussed it more in the paper. I think a very important part of it is that there may very well be a fixed cost of choosing a detour route at all. And so that is, I'm attributing all of the choice between a normal route and a detour to value of time difference between the two, but there might be this fixed cost. In the paper, I show for different assumptions on the fixed cost how much that impacts it. And so, of course, it depends highly on this fixed cost. The other parts that I mentioned, though, is that this is relative to Google Maps time, so it's going to be different in subjective time. And also, a lot of the estimates, not all, but many of coming from developed countries, are based on stated preferences. And so in this sample as well, when I ask people things exactly like the experiment, so if you have these two routes, one takes half an hour, the other one 35 minutes, one of them is costs 50 rupees, what would you do? The value of time implied by those exercises is significantly smaller. So I think there's also a discrepancy between revealed preference and stated preference. Regarding question of commuting alone, that's absolutely right. So I do not measure that. I do want to highlight, and so I think in general, this would affect the results. So you could think of more carpooling as response to citywide congestion pricing because people share the costs. That's not something I can, not an elasticity that I can measure here. One thing that is important though is that 2/3 of the sample is going to, more than 2/3 is motorcycle drivers. So they're generally going to be traveling alone. The question about fuel is also excellent. So it's something that I've done back of the envelope calculations, suggesting that for the difference in distance between these two routes, this would be very negligible, like 100 times smaller than the congestion charge the area charge that I imposed. But this is a good nudge to make that more formal and to include it. Thank you.
Wonderful, thank you. So I can see Clemence, Nick, and Marta have your hands up, just perhaps in the order in which you appear, if you would like to ask your questions, and then give Gabriel the last couple of minutes to answer those.
Sure, I'm just going to stop my. Oh, sorry. Go ahead, Clemence. Sorry, I'm at the top of my list. Go ahead.
Okay, should I? I'm sorry, I didn't know in which order.
You're appearing, sorry, Clemence, Nick, Marta here. Should we go for that order, if that's all right?
Okay. Sorry. Yeah, I have just a quick question on the short run, long run reaction of drivers. So I don't know if you have any room to look at this in the experiment, but my worry is that on the short run, you may have some like habit cost, and it may take time to adjust, but it doesn't mean it's actually costly. It just takes a little bit of time. And on the long run, you're actually okay switching road or switching times. Yeah. Or you could think about the opposite, where on the short run, you think it will be easy, and then you realize it's actually a big cost, and then you go back to your previous habits. So do you have any sense of how people reacted, and if they reacted differently just after the intervention and a bit later?
Thank you. That's excellent, and you're absolutely right. I think those are the two. It could go either way, and ex ante, I don't think we know. I don't have any results after the experiment. People dropped off because we were putting in some effort to keep them using this app consistently. So there's not data after the end of the experiment. What I can say is how these treatment effects vary by time in the experiment. And so for the area charge, which was 5 days, remember they had 3 days before, which I didn't talk about much, which were kind of practice rounds. So for the 5 days, the treatment effects are very flat. For the departure time charge, which was 3 weeks, it kind of builds up and it's constant in the second and the third week. And thank you again. These are results I have actually in the slides, but not in the paper. Yeah, but so that's all I can say, I guess. Even, of course, within these, even if it's a constant short-term effect, that's not fully at all addressing the question of how it would be if this is something that would happen for a year or 6 months.
But you don't see lots of people switching back to the reverse.
Oh yeah, no, I see no evidence of decreasing.
So because it could be on the short run. If you realize it's super costly, you go back. So it seems to say that there is no such effect.
Yes, you're right. Yeah, that's right.
Thank you.
Thank you.
Thanks, Gabe. So I have two questions and then kind of a comment that builds on some of the other stuff that's been said. The first is kind of about geography. So we've had some questions about equilibrium effects, some of them around geography, some of them around firm's response. And I think, the right way to think about it is the way that you outlined, is that, these things are going on in the background, but you're just focusing on the first order effects. But I did wonder about kind of the route choices and the spillover across different routes. So even if you were keeping residence and location fixed and house prices fixed, you could still have geography playing a very interesting part in terms of optimal policies, is that in that cities that look different in terms of their road infrastructure and their employment and residential locations may have very different optimal policies by the planner. The second question is about the kind of functional forms of the penalty, like the from the monetary costs. One thing that I found, I'm not sure if I'm interpreting this wrong, but interesting from that intensive margin RCT, where you kind of charge people incrementally according to the hour that they leave, it appeared that there was kind of a big bump in people leaving just before the fee came in. So it made me think about whether, you know, if you think about how congestion charge would work, whether a lot of this is happening on the extensive margin, like whether you are charging in that, you know, the peak, the charge-free time versus the charge time, and actually the variation in the fee within the window, whether that may have less of an impact or a different impact. And then the last question was kind of just building on what Clement said. I think these long-run elasticities are really important. And like when we think about congestion charges in the real world, I thought that extensive margin experiment was really interesting, because often, you know, the point of these policies is to try to get people to use public transport, which is just this fundamentally different technology that has increasing returns to scale. And, you know, I think if you look well, I can speak for London, but you see very large increases in public transit. So yeah, I'm not sure how that you can get at that, but you've done,
yes,
you have a little experiment to do it.
We might, just in the interest of, we're just very slightly over time already, so we might, if it's all right with you, Gabriel, turn to Marta's question and then maybe just a very quick wrap-up response to both, if that's all right.
Perfect, thank you.
Perfect. Thanks.
Hi, thanks, Claire, and thanks, Gabriel. So I hope you can hear me fine. My
yes.
question is about the asymmetries that you find in the results. So I found super interesting that you do find results for the morning reaction, but not for the late afternoon. And it seems that you also find that the cost of arriving early is larger than the cost of arriving late. So I was wondering if you could do some checks on whether the direction of the trip matters, whether arriving late to work is super costly, arriving late home is less costly, and vice versa. I think that would be quite clarifying, like, interesting.
Thank you very much. Let me start with that, kind of quick answers. I think that's a great idea. Unfortunately, so in ideal, I would want to do the discrete choice estimation in the afternoon as well. Unfortunately, kind of the reduced form results are less precise there. There's, you know, some evidence of a decrease in the number of trips too. So something I need to think more if I can do. So far, I haven't found that I can with the experiment that I have. Thank you. And very quickly on Nick's point. So I think it would be useful to talk more. I'm not sure I understand the route choice, kind of the gains coming from route choice. One thing that's relevant here is there's a strand of models in kind of computer science, basically looking at the inefficiency of routing on a network. And coincidentally, with linear costs, there's this whole set of results showing that routing is not very inefficient. So it's called the price of anarchy, and that, I mean, I think that may have a bite in this setting as well. The bunching right before, like at 0 charges, I think that's just kind of, I don't think that's something that's happening. I think there's noise in people's departure times, but again, happy to talk more. And I do agree very much on the long run. So I want to just summarize one last thing is, I think what this paper shows is that in this setting, there are no major gains from reallocating when people travel, which at least for one, I had more optimistic priors about coming in. I think this is not a paper saying congestion pricing should not be done in general. Thank you. Thank you all.
Terrific. Thank you very much indeed, Gabriel. Thank you to all the panelist participants for the level of engagement, interesting questions and discussion. We're really grateful, and we hope to see you next time and for the rest of the seminars in this series.